Okay, this week's agenda, we'll finish chapter 4, and then I've decided to, once we finish with chapter 4, I think the more relevant chapter for you to learn for this class is between 6 and 7, I believe. Yeah, I think chapter 7 will be more relevant. So we'll start chapter 7 today, after finishing chapter 8. And then we have lab number 6 today. It will be on three-phase inverter. We'll go over that today. But there won't be any lab report. All you need to do for this week is to simulate the example that we have in the book. And so you can learn how to build the circuit, how do you produce AC from DC, three-phase, and all you need to do is to show the schematic and the output voltages, and that will be it for this week's lab. Right? And then I'm hoping that's going to be half the lab session this week. The rest of the session would I'm hoping that you could still continue working on the final project, which I will talk about in a moment. And then weekly assignments this Friday. If you attended the presentation last week, you don't need to do the homework. You get a pass. So if I've already put the 10 points for those of you who attended last presentation. Presentation last Saturday. So please verify if you get the points. If not, let me know. And then quiz number 7. Oh, by the way, homework number 7 is the last homework of the quarter. Same thing with the quiz. Quiz number 7 is going to be the last quiz. I'm not going to give you any homework for next week as well as quiz for next week. So this will be the last homework and quiz assignments. For quiz number 7 is going to be covering chapter 8, specifically on multi-level, three-phase square wave, and PWM inverters, right? Chapter 8. Any questions on this week's agenda? All right, and then there's been a lot of questions and challenges in doing the final project. So I've decided to make it a lot less, constraints for the final project. So these are the 5 requirements that you will have to meet for the final project. So please, you can not ignore, but skip the other or ignore the other requirements, but focus on these 5 requirements, which are the same as the initial requirements, except you can now ignore the rest. Okay. I think the main objective of this final project, when I first planned it, was to see how you can apply what you've learned in the previous classes as well as in the previous EE411 to come up with hopefully some creative solution to be able to convert from high voltage to low voltage, right? And I explained this to some of the maybe groups. I don't think I explained this in the entire class. That this is not just a made-up project, right? I didn't make this up, right? This is actually a real-world project where the input is, truly from 5 to 6 kV, and the output is 12 volts at 50 watts. So this is coming from a real-world project, and I'm challenging you. At least that was the plan, right? Challenge you in hopefully coming up with some creative solution for this type of applications, right? Because it is a challenge, right, to go from very high voltage to low voltage in many aspects, as you already know. So those of you who've already started and struggle through the design, you know what I'm talking about, right? So there's so many aspects that you have to consider when designing high voltage to low voltage. And if you attended the presentation last week, Dr. Danet, he also kind of inferred the importance of knowing high voltage application, because that's the key in future electrical systems, right? Not just this type of application, but in future applications, because higher voltage gives you lower loss, right? So electric vehicles, that's the context he was talking about. The same thing, right? The DC system is high voltage, right? Maybe around 500, 400 to 600 volts, right? Going to very low voltage again to keep the cabling size, and keep the size of the wires tiny, right? Because if you can boost the voltage, then for the same amount of watts, the current is small. That's how you would reduce the size of the wiring. Therefore, you can come up with a more compact and more lighter electrical systems, right? So I think this would be a good. I thought it was going to be a good experience for you to at least try or attempt to design for this class. That was the original plan, and the specific application for this project is for underground fiber optics power supply. In case you're wondering, you can Google this yourself, that if you are installing or if you're running fiber optics undersea for miles and miles away, between islands, between continents, and these are all long distance, or basically long distance fiber optics cable under the sea. Then they would require, this fiber optics cable would require sensors, right? Mainly two sensors, thermal sensor and pressure sensor. And these sensors, of course, as you know, would require power, right? They require power to operate. And so how do you supply power? Fiber optics itself, they don't carry, they're not there to supply power, right? They're there to exchange, to transmit data, right? But not power. So then how do you transmit power along with this fiber optics cable to power these sensors, right? So what they do, again, you can Google this this topic. What they do is they would put high power, high voltage power equipment on both ends of the optic cable, right? So if they install the fiber optic cable from point A to point B, then they would put this high voltage equipment, power supply equipment on both sides, on both ends, right? So they would supply power into this cable, and has to be high voltage, right? Because imagine this is long distance, transmission of power. So if you use low voltage, then you're gonna have more currents, and more currents with long wires means more loss, right? So if you use low voltage before the power gets into the sensors, the voltage already drops so much, right? If you don't use high power. So that's the reason behind this 5,000 volts to 6,000 volts supply, right, for these sensors. And then at the point of the load, right? So at the sensors themselves, these sensors, they are not high voltage, right? They're operating at low voltage, so most likely 12 volts. So that's why you have to convert from this high voltage to 12 volts, right? And they're running multiple sensors. So usually one power supply will be able to provide power for multiple sensor at a single node. All right. So that's the application of this final project. Okay. So don't think that this is just me trying to give you a hard time, but this is an actual project, and I'm challenging the class, right, to be able to hopefully again apply what you learned, right, from previous class, and see if you can be creative in solving this type of problem. Okay, so from high voltage to low voltage. Some of you, I think, no, a couple of you in this class is actually doing a project for senior project that goes the opposite way, from low voltage to high voltage. Same kind of challenge, but yeah, same kind of challenge, but different type of applications. Right? So yeah, again, in my opinion, I think high voltage would be one of the future trends in electrical systems. I think it's good for you to get exposed to different aspects of high voltage design, right? And the other thing, the reason why I chose high voltage, because this is going to be simulation based only, right? If it's a project where you have to do a hardware prototype, I would never assign this requirement. Right? It would be scary to actually build it in the lab, right? So those are the main two reasons why I assigned this project. Because this is simulation based only, and this is a real world project, which is good for you to get different perspective, right? Different experience, different angles of DC to DC converter, right? Okay, so for those of you who have started this project, you already know the challenges that you have to go through to design this. So anyhow, so I've changed the number of requirements. Majority of them you can ignore now, and just focus on these 1, 2, 3, 4, 5. Okay, input voltage is still 5 kV to 6 kV with nominal voltage of 5.5 kV. Average output voltage is still 12 volt, so I've not changed these two. Plus minus 0.1 at 50 watts. Same thing with ripple, has to be less than 5%. Load regulation less than 3%, and finally line regulation has to be less than 5%. And then again, since this is simulation based, I came up with this rubric that now you can use to evaluate your design in terms of points that you'll get. These are all minimum points, right? Beginning of the quarter, I ask you to use the Excel sheet, right? To again evaluate or score your design yourself first before you demo it. But other than using that, with all of those requirements, since I'm I'm eliminating some of the requirements. Now I have to come up with a new rubric. So here's the new rubric right here, right? These are all minimum points. So if you could get those requirements, right, where all the components that you use in the simulations are all ideal, which you are allowed, right? Then the minimum points you'll get, of course, if these are all met, okay? Then the total points that you get minimum would be 75 out of 100, right? And then if you use some models as a real world model of the components, let's say 75% of the components you use in the simulation is ideal, then the minimum you get is 81 out of 100. Again, assuming that you meet all of all these three requirements, right? If it's half ideal, then minimum is 87. 25% ideal, meaning 75% of the components, roughly, okay, roughly 75% real model of the components. Then you get 93% out of 100. Again, these are all minimum, okay. And then if all are real model of the components, if you use every single component to be a real model, then you get 99 out of 100. All right, again, these are all minimum. And then in terms of creativity, right? If this is very subjective, of course, I'm the one who would determine whether or not the method that you use is very creative, right? Is at least creative in my opinion. Then I would give you at the most 5 points as bonus. Okay, so we'll see if any of the groups can come up with creative solution to do this, right? Any questions on this? Oh, before I do that, before I answer any questions, and then deliverables also have been changed in sort of the ones that I have in the syllabus. Now you just need to demo your simulation, and you need to show me all these three things, right? Output voltage, line regulations, load regulation, right? And then, yeah, I prefer you do the demo during lab sessions next week, or you could also do it outside of the lab sessions. But if you do that, you need to schedule an appointment with me, so we can schedule a time for you to demo your simulation. But these have to be done before the deadline, which is the Friday of next week, Friday, before 5 p.m. Are there any questions on this?
So there's no PCB requirement or any of that anymore. We're just doing a big simulation and demoing that.
Right. No more PCB, no more cost, none of those. So just focus on these requirements.
Awesome.
Then,
okay, thank you.
Yeah, and then simulate it, and then you just need to show me the simulation, your circuit, right? And then show me the output voltage, line regulations, load regulations. Are there any other questions?
I had a question.
Yeah.
I don't know if I'm just missing it, but it doesn't look like there's an efficiency requirement anymore.
Right. There is none.
Okay.
Yeah. The efficiency is going to be tough to define, because then I'm allowing, because this is simulation, so some of you will be doing all ideal, 75% ideal, and so on and so forth. So I have to come up with more,
I'm really happy to hear that, because I got mine up to about we got the design up to about 70% with all real models, and that was like brutal. So
yeah. yeah. So it is tough. It is tough to get a very efficient system when the distance between the level of voltages between input and output is very far, such as this one, right?
Yeah, I never realized that, like, even a sub-ohm base, or like sub-ohm, on resistance of a device actually starts to matter when you put like 10 of them in series.
Absolutely, yes, exactly. Yeah, so those are the different aspects that you learn while you're doing this, right? Which maybe you don't appreciate before, but now you understand the importance of, this, just like you said, the small ohms, small resistance now becomes a critical parameter when you have, devices in series, for example, right? Okay. Are there any other questions? Okay, let's continue our discussion on multi-level inverters. I explained last time that the modified square wave that we covered in EE411, right, was useful because we can lock into a certain harmonic locations and eliminate that harmonic noise, right, based on alpha. And depending on which harmonic location you want to get rid of, that would determine what alpha value that you need to use, right? And here's the equation for alpha, 90 degrees over n, where n is the harmonic number. So if you want to get rid of harmonic number 3, for example, 3 times 60, so that's 180 hertz component in a 60 hertz system, then you need alpha to be equal to 30 degrees, right? 90 degrees divided by 3, that's going to give you 30 degrees. So you need to apply alpha to be equals to 30 degrees, right? So that's useful, really, right? Especially with a square wave, when where odd harmonics are really dominant, and number 3 is very close to the fundamental component, right? And I don't know if you remember from EE411, but if you have a square wave, you will have only odd harmonics. There is no even harmonics, right? So 1, 3, 5, 7, 9, and so on and so forth. There's no even harmonics there, right? But number 1 is what you want, right? That's the fundamental components. That's a 60 hertz. Number 3 and so and beyond, those are not desired, right? Those are noise, basically. And so you would like to minimize those. And another problem with square wave is that the way harmonics, the way Fourier series, if you derive the Fourier series of a square wave, such as this one, then the magnitude of these harmonics becomes smaller as the harmonic number increases, right? Meaning harmonic number 3, which is the closest to 60 hertz, will have the biggest, amplitude among all harmonics. So it is useful to have this kind of this technique where you can actually get rid of the highest harmonic in the system, right? The highest noise in the system, simply by applying alpha equals to 30 degrees, right? Okay, so then in order to improve the quality of the output voltage, because if you can see here, right, if you look at the screen here, right, that doesn't look at all like a sine wave, right? And for some systems, this is acceptable. In fact, if you buy like a cheap inverter, right, the one that costs you maybe around $30, $45. I just purchased recently for my car, right? So you plug in into the 12 volts, DC source in the car, the DC plug-in, right, in the car, 12 volts, and the output is AC to power my laptop, for example, or any AC load you have in the car. And me being an electrical engineer, I actually went to the lab and look at the waveform of the output of these cheap inverter, and guess what this cheap inverter gives us in terms of AC? Exactly this. And you could kind of tell that they're targeting 30 degrees as well out of this cheap inverter, right? So that's exactly what I have for my inverter that I have in my car, right? This type of waveform. And for that kind of, for most, not for most, but for some applications, having this shape should be okay. The reason being, if you think about power supply, right, for your laptop, for many of the electronic or portable electronics, right, this AC has to be converted to DC anyways, right? Because internally these portable electronics are operating in DC. So having flat AC like this would be okay, because imagine if you rectify this, right, then you get more flat DC, right? So except that you're going to have gaps as well, which you can filter, right? So for some application, having this shape is fine, right? Especially if you rectify this and then you filter it, right? So that should be okay. But then for other application that require sine wave, right, such as motor, for example. So if you connect this to a motor, right, then that's going to be a problem. A motor expects you to supply, sine wave as much as possible, right? Reason being, you have different voltage applied to the motor, and the way magnetic field is being produced in the motor, which create torque, right? Imagine if the applied voltage looks like this, then you have some kind of spinning of the shaft of the motor that is not smooth, right? Because of this shape, right? So what do you call it? Like a cogging, maybe? Like a torque ripple instead of electrical ripple, instead of voltage ripple, it will have a torque ripple, right? If the voltage is not smooth, right? And other loads as well, they are sensitive to sine wave. They would have problems seeing this type of waveform, right? Many AC equipment such as transformer, right? They are looking for sine wave, not this type of waveform. So then the question is how do you improve the shape of the waveform? And we went over this last week, right? That we can add more levels, right? As you can see, by adding more level, by introducing more alpha, you could get more sine wave like output voltage, right? And imagine if you have more steps, then you got output voltage that is closer to being a sine wave. So I think I mentioned this last week as well, that in AC applications, right, involving AC equipment, which are expecting a sine wave, it is not uncommon to have a square wave that has 48 level, 72 level. Imagine if there's 48 levels here, then you can see that that the the waveform will be looking like sine wave even more, right? So it's closer to a sine wave the more steps you introduce to the waveform, to the square wave, right? So sticking with this example where I have two levels, two alphas, right? Two DC levels. You can see that the equation for Fourier series for that waveform consists of two alphas, right there. So mathematically, again, for this example, okay, you have output voltage, right, in time domain with respect to time is equal to the Fourier series, which is also with respect to time, right? So we are using Fourier series to represent the function of this waveform. And as expected, the Fourier series consists of alpha 1 and alpha 2, right? And this is calculated, right, for n, this is Fourier component, equals to 1, 3, 5, 7, as I said earlier. Since we have a square wave, the even number of harmonics are gone, only the odd harmonics, right? So 1, 3, 5, 7, all the way up to infinity, if you like, right? And then you can see that for every harmonic number n, right, you have to calculate this term right there, cosine of n alpha 1 plus cosine of n alpha 2 times sine of n omega t over n, right? And notice that for every n, every harmonic number, it has this coefficient, meaning this value that I'm going to what do you call it, enclose with this loop right there, right? These values are constant, right? So cosine of n alpha 1 is a constant value. So cosine of n alpha 1 per given n will be a constant value, right? Same thing with cosine of n alpha 2 will be another constant. And then n will also be a constant. So this is what we call coefficient, right? Right. So all the terms that I encircle right there, that's a constant, right? That's called the coefficient of the Fourier components, right, for each n. Okay. So therefore, if I look at specifically just the coefficients of this Fourier series, then you have this equation right here, which hopefully now makes sense. Now you have coefficient for each n, harmonic n is equal to 4 times VDC right there, right, from here, times cosine of the one that I just encircled right there, right, divided by n, that's right here. Okay, so this equation that I have right there gives you the coefficient of the harmonic number, which in turn gives you the magnitude, right? Because it's constant, right? It gives you the magnitude of each harmonic number. If I erase this whole thing, right? So you see every sine wave will have magnitude, right? So now we have the equation for the magnitude of each of the sine waves in the Fourier series. Right? Here's our sine wave right there with respect to time, right? So every single sine wave in every single harmonic number will have this magnitude right there times the 4 times VDC divided by pi, right? So this times this, right? That term times 4 times VDC divided by pi times cosine of n alpha 1 plus cosine of n alpha 2 divided by n, that gives you the magnitude of each of the sine waves in the harmonic number, okay, per Fourier series. Does that make sense? All right. Now, why is that important to know? Why is it important to know the equation for the magnitude? Well, because when we are designing inverter, we need to know how much output voltage, RMS wise, we're going to get on the output, right? You're designing an inverter from 100 volts DC, and you'd like to know, okay, I need to get an AC output that has 50 volt RMS, right? And that 50 volt RMS will be determined from the magnitude of the Fourier components, right? More specifically, the fundamental component, right? So V out 1. So if you do n equals to 1, right? N is equal to 1 means we are interested in the fundamental component of the output, which we are interested only in the fundamental component, right? So from this equation, right, I could get the equation for the magnitude of the fundamental component. And we can use this equation as one of the criteria for designing the inverter, right? So that's a criterion that we can try to target when designing an inverter. I want the RMS of the fundamental component to be such and such value. Right? Okay, and then more specifically for multi-level inverter, we define what we call modulation index, MI, which is defined to be the ratio of the amplitude of the fundamental frequency component of the out to the amplitude of the fundamental component of square wave of amplitude to VDC, right? So we have input that is VDC, right? That creates the square wave. And from that input square wave, we get the fundamental component of it, right, from the input. And then on the output, we have the modified multi-level square wave, which has its own equation for the fundamental component of the output, right? So therefore, the ratio of the two, right, the ratio of the fundamental component of the output to the fundamental component of the input square wave, right, due to the DC, that is called modulation index, right? So that's the definition of it. And now we know the equation for the out one, right? So now you know why having this equation is important. Now I can plug in that equation into here when n is equal to 1, right? And divide it by 2 times the fundamental component of the input, right? And that equation simplifies to this equation right here, right? So using two DC voltages, modulation index becomes, you know, this equation right there. All right, and then actually I rewrite the equation this way. So from MI is equal to cosine of alpha 1 plus cosine of alpha 2 divided by 2. I rewrite that equation to be this way, right? That cosine of alpha 1 plus cosine of alpha 2 is equal to 2 times MI. Keep in mind that MI is the ratio of the fundamental component, right, of the output over the input, right? So this will give us the RMS of the output voltage. Okay, that's one criterion. Another criterion is that we also would like to be able to choose a certain harmonic number from alpha 1 and alpha 2, right? And get rid of that harmonic number. Remember the noise I was talking about, right? For example, the third harmonic. So harmonic component and its multiples can be eliminated from the output voltage waveform with proper selection of alpha 1 and alpha 2, right? Just like the square wave, modified square wave we had in EE411. If you pick, you know, alpha to be 90 degrees over n, you can get rid of harmonic n, right? Same thing here. If you would like to get rid of harmonic number m, then you have to pick certain value of alpha 1 and alpha 2, right? So that's another criterion, right? And mathematically, that means cosine of m alpha 1 plus cosine of m alpha 2 has to be equal to 0. Why is that? Well, if you go back to this equation right here, yeah, right there. Let me erase, right? So again, that's another reason why this equation is important. In addition to giving us the criterion for choosing or targeting RMS of the output voltage, by using the same equation, I could also log into a certain harmonic, see, n is harmonic number, right? And get rid of it, right? So if this equation is equal to 0 for that particular n, that means I'm getting rid of that harmonic level, right? That harmonic component, n, okay? So how do you get this equation to be equal to 0? Well, 4 times VDC, that's a fixed number. You cannot, you know, force it to be 0 unless the input is 0, but that's not the case, right? The input is non-zero. N is not going to be non-zero value. Pi is a constant value. So the only part of the equation that we can force it to be 0 is this part of the equation, right? So if this part of the equation is 0, the product of the two will be 0. That's why for the criterion of locking to certain harmonic number and get rid of it, right, you can get it from this criterion right there. For harmonic number m, right, if you have cosine of m alpha 1 plus cosine of m alpha 2 to be equal to 0, that means I can get rid of that harmonic number m. Right. So in summary, I could have alpha 1 and alpha 2. If I choose those alpha 1 and alpha 2 properly, then I could achieve two things. Number one, I could achieve a desired RMS value of the output voltage, and at the same time, I could eliminate certain harmonic number. Is that cool? Right, so I could achieve both, but by choosing alpha 1 and alpha 2 properly. Okay, so that's
something I'm a little confused on. Oh, sorry if I interrupted.
No, go ahead.
I'm a little confused on like eliminating the main harmonic, because like the purpose of like the inverter is to kind of output a square wave of like the same, or not a square wave, output like close to sinusoidal as possible. And wouldn't the mth harmonic be kind of what shapes that output? Like that's kind of what you would want instead of not want?
That's correct. That shapes the output, the original output, right? Right here, for example, right? Let's say that the shape of the output is this way. That's correct. That is being constructed. This is being constructed by harmonics. But what we want is not this. What we want is this, right? What we want is this. You agree?
Yeah.
Right. So then how do you go from square wave to a sine wave? You filter it, right? You filter it. But you agree with that?
Or wouldn't the fundamental frequency be the frequency of the sine wave instead of the square wave?
Exactly, yes. So the blue, if you look at the Fourier components of the blue, come on, okay, blue. If you look at the Fourier components of the blue, it will be like this. So you have the first component, harmonic number 1, and you have harmonic number 3. This is frequency domain, okay? This is frequency domain. And then you have the fifth, right? And the 7, and so on and so forth. You agree? That's the square wave.
Yeah, that makes sense.
But the red, right? The red, if you look at the red, if it's a pure sine wave, it's going to be looking like this. And that's it.
And the square wave harmonics would be more to the right because they're...
No. The harmonics is still there. What we're doing here is that we are blocking this harmonic that way using a low pass filter, for example.
So when we talk about the square waves, are we talking about to the individual like steps, or are we talking about, because I'm thinking that like you could like add up like the like a bunch of squared pulses, and then that would give you your harmonic content. But like the sine wave is like a much lower frequency. It's because it's less abrupt changing.
Yeah, the sine wave is a pure sine wave. That means it only has one frequency component, which is at 60 hertz, right? But if you have a square wave, the final square wave, not individual square wave, not the individual square wave that you are adding, you know, this is the final square wave after you add them, right? They will have these components.
Oh, you're just talking about one of the square pulses, but you're adding multiple together.
That's correct. Yeah, this is the final square wave, the final waveform. The blue that I'm drawing right there.
Without filtering.
Without filtering, yes. Right. So then the objective here is that how do you select alphas such that you get something similar to the blue, something similar to the steps, but it could get rid of number 3, for example.
Oh, by setting that by that equation.
Exactly, by choosing proper values of alpha 1 and alpha 2.
And then it's easier to filter 5 and 7 than 3 because it's farther away from the fundamental.
You got it. You got it. Okay. Does that make sense now?
Yeah, that clears everything up.
Okay. All right. So yeah, so what I'm saying is that with a multi-level inverter, it is also still possible for you to lock into a harmonic location and get rid of it. That way, the low-pass filter requirements will be what do you call it? Will be light, right? You don't have to put heavy filtering. But imagine if the tree is still there, right? Imagine if this harmonic number is still there. You're gonna have to use, big inductors, big capacitors, right, to get the right cutoff frequencies. But if number 3 is eliminated, and then the next harmonic will be number 5, right? That's further away from 60 hertz, so it'll be easier for us to filter. Okay.
That makes sense.
Okay, good.
Wait, so like the modulation index would be kind of the sum of the square wave components divided by the output sign, or what was it again? Or the equation's right there, but that's what it means.
That's fine. Yeah, modulation index is the peak or amplitude of the fundamental component of the output without the filter right here. So the ratio of that, that's the peak value right there, right? Let's say that peak value is the out peak divided by twice the peak value of the fundamental component of the input, P out 1 in. Right? So the input is a DC input, but this DC input is creating the square wave. Right? So if let's say the input is like this, plus VDC, after you create the square wave, right? Then this square wave has the out 1 as well, right? Fundamental component.
Right.
Value, that's the one that goes on the denominator right here.
Oh, I see. And the sign would go underneath it, like it would, because it would have to be underneath the source. But that, so it's that ratio or the peak.
Yeah, yeah. So you are comparing the peak of the fundamental component of the actual output, which has multiple levels, to the input, which has only 2 levels, 1 and 2.
Oh, I see.
Yeah.
So it's possible to have, or it's not, is it possible to have a modulation index greater than 1?
Without transformer, no. If you have no transformer, then I don't think you could have that. Right? So the short answer to that is no. Yeah, because the input should have the largest peak than the output.
Oh, right. It just can't supply more than it's.
Right, exactly. Well,
without a converter that steps it up.
Exactly, unless you step up the input. Exactly. If you don't have anything else in between, you don't have a boost converter between the input and the inverter, or you don't have transformer after the output, then modulation index should not go beyond 1.
That makes sense.
Okay, very good. All right, so then let's see. Here's an example. Let me erase this. So you see we have, for this example, multi-level inverter, input voltage 50 volts, determine the Fourier coefficients through n equals to 11, for alpha 1 equals to 20 degrees and alpha 2 equals to 40 degrees. So those are the alphas. And part B, alpha and alpha 2, so determine alpha 1 and alpha 2, right, such that the third harmonic is eliminated and modulation index is 0.8. So now we have the 2 objectives, right? Using the 2 criteria right here, using the 2 equations, right? Eliminator harmonics and modulation index of 0.8, meaning the RMS of the output is going to be 80% of the RMS of the input, right? So for part A, that's just plug in Chuck. You have the equation for the coefficients, right? So n is equal to 1 until 11. So you can see that the number 1 by plugging n equals to 1, that's going to be 108.591, and so on and so forth, right? You can see for that angles, for those angles, 20 and 40 degrees, you can see that the third harmonic is practically 0, and then the 9th is also 0, right? But the other ones are not. All right. And then for part B, this is where we want to achieve those two targets, right? Modulation index 0.8, and we want third harmonics. So that's so m is equal to 3. That's why I plug in m equals to 3 right there and right there as well, right? And then you have two equations, two unknowns, right? So two equations, two unknowns, you should be able to solve it. And I use MATCAD to solve this. And in MATCAD, I have to provide initial guesses for those two alphas. And I just type the two equations. That's why I like MATCAD. You just type in those two equations and it'll find it for you right there. Right, so alpha 1 and alpha 2 needs to be, there need to be 7.482 and 52.518 degrees, such that if you choose those, then it will meet those two requirements. Okay. Any questions on this? And you can definitely extend this from two different DC values to more DC values, right? And if you do that, then of course the equation becomes even longer, right? I won't go through this, but it's the same procedure over again. You can do the modulation index, right? Now it's in terms of many alphas, right? Because you have more levels in the output. Oops. Yeah, and then you can also apply, the what do you call it, harmonic eliminations, right? If this equation is equal to 0, then you have the second criterion for eliminating harmonics. So now you can solve, hopefully solve the problems that way. Here's an example of 4 different DC voltage sources. These DC are at different values. Actually, yeah, it is. Oh, actually, no, they're the same DC levels. Sorry, they're the same DC levels. As you can see, they're the same DC values, but then it's connected to different modified square wave, right? So 4 different modified square wave whose output are being series to give you the total output, right? So if that's the case, then I have even better output waveform that looks closer to a sine wave, right? Here's the output of the first one, output of the second inverter, output of the third inverter, and the fourth inverter, right? Every single one has different alphas, and if you add them up, you get these waveforms. Of course, I can always adjust alphas. This one looks like more like a triangle, but if I fine-tune the alpha, you can definitely get a more sine wave-like waveform. Okay, but hopefully it's clear to you that the more levels that you have and applying proper alphas, you get much better quality of the output voltage, right? Just like I said earlier, for AC application, utility scale application, 48 levels, I've seen 48 levels, and I've also seen 72 level of this inverter, right? A lot. Okay, now in practice though, you're not going to do this, right? You're not going to do this in real world application. In order to get multi-level, you don't do this, right? You don't want to have separate DC sources, and you don't have or you want to avoid having 4 different converters, right, to create the 4 different levels, right? That's going to be costly and not efficient at all, right? So in real world implementation, we use much better topology than that one, much better method than that one. So rather than having separate inverters, we use just one single topology. Isn't that cool? Right there. So here's an example where we have one single topology that would create, is it 5 level output? Yeah, it is. Yeah. So you have a 5-level output inverter using only one source and one topology, multiple switches, but one topology. And instead of having several inverters, several individual inverters, and then add the output together instead of doing that. This is a much more efficient way of achieving multi-level, right? And how does this work? Well, you have to time or control the signals, time them correctly to give you the levels. And this is an example of how you can achieve, for example, the positive half cycle of the output. The output itself will have 5 levels right there, right? It will have plus VDC, 1/2 VDC, and then 0, minus half VDC, and plus minus VDC. So something like this then, right? Something like this. But this is the 0, okay? So VDC over 2, and then plus VDC, and then 0. And then minus VDC over 2, and then minus VDC, right? So that's 5, those are 5 levels. Right? Here's an example of how you would control the switches, how you would produce the levels for the positive half cycle, right? Only for the positive half cycle. The other half cycle, which is negative, is going to be just the opposite of this, right? Or it's going to be similar to this, but for the other half of the topology. So you can see we have 2 halves of the topology. We have the left half of the topology and the right half of the topology right there. The left would give you the plus half cycle, the positive half cycle. The right will give you, the right portion of the circuit will give you the negative half cycle. So here, this is just showing you the table to produce the positive half cycle from the left side of the circuit, okay? So let's see, how do you create 0 on the output? Oh, not output, sorry, VA, right here. VA is right there. How do you create 0 on that? Well, that could be done by turning off S1 and S2, and then turning on S1, S3, and S4. Right, so right here, turning off S1 and S2, and turning on S3 and S4. You can see that by doing so, this node, which is VA, is pulled to the ground. Right, this is the ground. Right, so that would give you VA equals to 0. All right, and then how do you get VA equals to VDC over 2? That happens when S0 is, so let's see, 0, 1, 1, 0. Okay, 0, 1, 1, 0. 0, 1, 1, 0. 0, 1, 1, 0. Okay, 0 meaning off, 1 meaning on, 1 meaning on, 0 means off. So that's 0, 1, 1, 0, right? If that's the case, what is the voltage at this node with respect to ground? Right there. Well, let's see. What is that voltage? How do I get the right? Okay, so this node right there, if S2 is on, a short, it's going to be the same as this node, yes? If that is the case, then the voltage from, let's say, X to Y should be the same as the voltage from X to VA, if this is VA, right? Because again, Y is equal to VA. Agree? So this node should be the same as that node. It's shorted right there. So therefore, the voltage from X to Y should be the same as the voltage from X to VA. What is the voltage at X? Well, that's VDC right there, right? But then we can see that the bottom side right there is also open. So if you go around this loop, go around this big loop right here, you can see that the open terminal voltage has to be equal to what? By KVL, VDC over 2. And this one is also VDC over 2. Do you agree? Yes? If you agree with that, then if this is VDC over 2 from here to here, and this VDC over 2, I should probably focus on the bottom one, not the top one. If this is also plus VDC over 2, then guess what the voltage is from VA to ground? Well, this node right here is shorted to this node, right? So therefore, we know that VA to ground is equal to this node voltage to ground, which is VDC over 2. Right? So hopefully that proves to you that if you have 0, 1, 1, 0, then voltage from VA to ground is it's equal to plus VDC over 2. Any question on that? How about the last level? How do you get plus VDC? So we did look at how we get 0, how to get VDC over 2. How do you get VDC? Well, VDC happens when we have 1, 1, 0, 0, right? If you do that, then you go ahead and use do a KVL around this loop, and you can see clearly that voltage across VA is VDC. All right. So by controlling those switches and time those properly, then you can get the 3 levels for the positive half cycle. Right? 0 plus VDC over 2 and plus VDC. Right? Using only one topology, which is pretty cool. Any questions on this? Can you go more than 5? Yes. You can do 7 levels. You can do 11 levels. Right? You can search on this in the IEEE Explorer, for example. Remember I said earlier that having 48 levels, 72 levels are not uncommon, right? So imagine how to produce those levels, right? With a minimum number of converters. Okay, so again, this is an example of a higher level circuit, just one example. There are more topologies to create 5 levels, 7 levels. I'm just showing you one example that can produce 5 levels. Any questions on this? Right. Okay, so now you know the additional technique to get AC out from DC, right? Using multi-level, right? Instead of just a simple square wave, right? You can also use multi-level inverters, and also PWM, right? Which is the end of this chapter. Are there any questions? If not, let's proceed with the next topic: three-phase 6-step inverter. So this inverter produces a 3-phase AC output from a DC input. Right? A major application is speed control of induction motor. The output frequency is varied, and the amplitude of output voltage may also be varied. So that's a typical application for a 3-phase inverter. The first is to connect this inverter to a Y connected load. So I have 3 phase loads, right? And then the loads are connected in Y connection. You'll see, or you can see from here. So I have the inverter, 3-phase inverter, input is DC, right? And then the load, the 3-phase, just like that one, and it's connected into a Y connection, as you can see, right? A Y connection has common node, right? So that's why I know this is a Y connected load. All right. And the switching sequence for each switch, I have how many? 6, right? So you have 3 legs right there in the inverter for A, phase B, phase C. If you look at every single switch, the duty cycle is 50% for every single switch. And I'll show you the switching signals on the following page. Switching action takes place every 60 degrees, meaning something happens at every 60 degrees while you change the state of the circuit, right? So 60 degrees, so 360 degrees is the full cycle. 360 divided by 60, that's 6. So you're gonna have 6 different states of the circuit, right? If you are using this technique. Switches S1 and S4 close and open opposite of each other. Right? This should be something that you already know. For each leg, the two switches cannot be on at the same time. Otherwise, you're going to short the input, right? So S1 and S4 cannot be on at the same time. Likewise, S3 and S6, as well as S5 and S2, they cannot be on at the same time. But at any given time, though, at any given time, you'll see 3 switches will be conducting, I should say. At any given time, 3 switches will be conducting. One from phase A leg, the second one from phase B leg, and then the last one is from the C, right? So at any given time, 3 switches are conducting from each phase. These are the switching signals right there, okay? And you can see the duty cycle is 50% for each, right there. And they're overlapping, right? At any given time, 3 of these switches overlapping, indicating that 3 switches are conducting at any given time. For example, from 0 to 60 degrees, you can see that S1, S5, and S6 are conducting, right? And on from 60 degrees to 120 degrees, S1, S2, and S6 are conducting. What did I say about the complementary switches? 1 and 4, okay? 1 and 4 cannot be on at the same time. 1 right there, and 4 right here. You see that? They're complementary, right? If one is on, the other one is off. Same thing with S2 and S5 looks like, right? S2 and S5 complementary. S3 and S6 also complementary, right? Any questions so far? So 50% duty cycle, 3 overlapping at any given time, right? And the overlapping, or not overlapping, but the combination, different combination of the 3 switches will last for 60 degrees, as you can see, right, from here. So we have combination of S1, S5, S6 for 60 degrees. And then we have combination of S1, S2, S6 for 60 degrees as well. Yeah. The first one is S1, S5, sorry. First one is S1, S5, S6 for 60 degrees. The second one is 1, 2, and 6. The third one is 1, 2, and 3, right? And so on and so forth, okay? Any questions so far? So then what I would like you to understand is this right here, that 6 different states. Why 6? Well, each state is 60 degree long, see that? Right, 360 divided by 60, that's 6 different states. And you can see that I'm only looking at the load, right? Because we are interested in the output voltage waveform, right? VAN, VBN, VCN, right? So this is what we need to look at. VAN, VBN, VCN. That's called phase voltages, right? How about line voltages? Well, line voltages is VAB, VBC, and VCA. Right? I could get this once I get the phase voltage, because I know that VAB, for example, that's just VAN minus VBN, right? So if I know VAN, I know VBN, and I would know VAB, right? So how do we determine VAN, VBN, VCN? Well, it would be determined from which 3 switches are conducting at any given time. For example, from 0 to 60 degrees, I said what? 1, 5, and 6 are on, right? So imagine that, 1, 5, and 6. If 1 is on, right here, right? And what did I say, 5 and 6? Oh, I forgot already. 1, 5, and 6, isn't it? Yes, 1, 5, and 6. Ah, come on. 1, 5, and 6. So 5 is right here, 6 is right here, right? And the rest are off. Imagine if we have that. Then you can see that this is our A load, this is our B load, and this is our C. Then you can see that plus VDC is connected to A, right? And then for B is the minus VDC. Yeah, that's B. So right here, that's connected to the minus, right? A is connected to the plus of the VDC. How about C right there? C is S5. So you can see that for C is connected to the plus VDC as well. So C is going to be connected to the plus, right? So when 1, 5, and 6 are on, A is connected to the positive side of VDC, B is connected to the negative side of VDC, and C is connected to the positive side of VDC. Is that clear from this picture? Yes? So if I draw that here, just the load side, okay? Then that's what you see, right? Right here. Right? A is connected to the positive, C is connected to the positive, and B is connected to the negative. You see that? You see that? So I'm redrawing the load, right? Now, why is it important to do this? Because now we can see clearly how much voltage we have for VAN, VCN, and VBN, right? If you have this situation right here where you have two resistors right there and one right here, right? These loads are balanced, okay? I forgot to mention, they're all the same resistor value, right? And do a voltage divider for this. Then how much voltage is appearing across the one by itself? That's gotta be 2/3 of VDC, you agree? And the one that has two in parallel, that's gonna be giving you 1/3 of VDC, right? So same thing here, you get plus VDC across all three, right? Plus VDC across here, and you can see the one in parallel, that should give you 1/3 of the VDC. That's why it's V/3. And then the one by itself should give you 2 times VDC/3. Make sense? But watch out for the polarity though. If I ask you to determine for this segment 0 to 60 degrees, what is VAN at this point? Well, VAN, right? A is right here, and sorry, and N is down here. See, N is right here. What is VAN? Well, VAN is going to be plus VDC divided by 3. What is VCN? Well, VCN, N is right here again. That's going to be plus V divided by 3 as well. But what about VBN? You can see that B right now, for B, the N is up here, right? And the plus sign of the voltage across B is actually tied to N. So therefore, for VBN, the voltage is not positive. The voltage is now negative 2/3 of VDC. Is that clear? Any question on that? So if I draw the waveform from 0 to 60 degrees, right? Then I know that for VAN, that should be 1/3 of VDC right there, right? Just flat. This is 0 to 60 degrees, all of these, right? And then for VBN, what did I say? Minus 2 of VDC divided by 3, right? Right there. See that? Minus or negative VDC/3 times 2. And then for VCN, it's the same as VAN. So that's 1/3 of VDC, positive, right? Positive value. So now you understand why I have those voltages for 0 to 60 degrees for VAN, VBN, and VCN. Any question on this? Let's do one more. The next interval, what do we have? What do we have the next interval? Well, you have to look at the switching signals, right? Take a look at the switching signals in your book, and let's look at it together. The second signal, second state would be 60 degrees to 120 degrees. We can see that 1, 2, and 6 are conducting. 1, 2, and 6. Let's go back to here. Now we have 1, 2, and 6. Right. So 1, 2, where's 2 right here, and 6 right there. Okay, so what can you conclude from here? Well, if 1, 2, 6 are conducting, then I know that A would still be connected to the positive of the input, right? You can trace that wire. B is connected to the minus of the input, right? You can trace the wire for B as well, right there. And then C, since number 2 is on, is also connected to the minus of the input. So now we have plus, minus, minus, okay? Plus for A and minus, minus for B and C. Let's see if that's what we have here. Yes, right there. See that? So plus for A only, and the other two are minus, minus right there, right? So now by having different switches conducting, you are changing how the load is connected to the inverter, which is clever in my opinion, right? So now you can see that A now is by itself. When A is by itself, you expose the terminal with the same voltage VDC. Now you know that AN becomes plus 2B divided by 3 because it's by itself. The one in parallel this time is B and C. So therefore, each of these will see 1/3 of the input voltage. However, the polarity flips, right? Because N is now connected, is also connected to the plus side. So therefore, if I ask you to determine VBN at this point, it should be negative of VDC over 3. Agree? Because again, the N is on the positive side. So knowing those, I could now continue drawing the waveform. VAN is 2/3, right? Positive, right there. So now you know, now you understand why from 60 degrees to 120 degrees, right? The level of the voltage for VAN is 2/3 of VDC. And then the voltage for VBN is minus 1/3 of VDC. And the voltage for VCN is the same as VBN, is minus 1/3 of VDC. Cool, isn't it? Right. Okay. So if you proceed with the rest of the signals, right? I won't go through the rest, but you should. Right. This is going to be your lab today. Right. If you time the signals this way, right? For the third one, it's 1, 2, 3 that are on, then it will change how the load is connected. Now you can see that A and B are in parallel, C by itself, and that would give you the next voltage levels right there, right? And if you do it throughout the entire cycle, guess what you get? You get a square wave, right? That looks like a sine wave, right? Follows a sine wave, almost like a multi-level, right? Multi-level inverter. Any questions on that? Okay, now once you get VAN, VBN, VCN, then you can always get the line-to-line voltage, line-to-line voltages, right? As I said earlier, if you have VAN and VBN, then you can get VAB. What is VAB equal to? VAN minus VBN. So go ahead and do that to draw the line-to-line voltage, right? Let's start from 0 to 60 degrees. What is VAB? Well, that's VAN minus VBN. VAN at this point is, at this point is 1/3 of VDC. So that's going to be VDC over 3. I'm doing 0 to 60 degrees, okay? And then what is VBN? Well, VBN right now is minus 2/3 of VDC, right? So go ahead and do the subtraction. What do you get? You get plus VDC, isn't it? You agree? So from 0 to 60 degrees, if I were to draw VAB, it should be plus VDC at this point. See that? Right there, plus VDC. And so on and so forth, right? So you can do the subtraction segment by segment, right? To give you VAB, VBC, and VCA. All right.